Yes, I want to tell you about a vector graphics language that I think some of you have heard called Asymptote. And recently it's been extended to 3D with lots of new features. And I want to tell you about those new features and a little bit about the history of the project. The work in this talk was done in collaboration with Andy Hammerlindell. Oris Chart did the PDF, the 3D PDF driver, and Mikhail has done recent enhancements on that driver. So those why those three are listed there. And this work was, much of it was done at the University of Alberta in Canada, and but also around the world. There are many active developers very busy on this in France and Germany and in Brazil. Andy is now in Rio, lucky guy. So this is some of the history of Asymptote. It was very strongly inspired by TeX and Metafont, and in particular the idea of a path, and we make direct use of the control point selection algorithms by John Hobby, and also the Knuth concept of a path. And so the history of this was, TeX dates back to 1979. The second version of Metafont, which has the control point algorithms I'm talking about, was in 86. And then in 89, Hobby realized you could take Metafont and instead of producing font data, you could actually, which was vector data at that point, it was no longer bitmaps in this year. And he realized you could produce PostScript with it, which made a lot of sense. And the only trouble is that Metapost was, being part of the TeX family, was limited to integer arithmetic, fixed point arithmetic. And that was a perfectly reasonable decision back in those days when the IEEE standard hadn't been standardized. It was around 85 or 86 when that was finally standardized. And so because this is a more modern implementation of some of the same ideas, we were able to build on top of the IEEE numeric format. And it's made it more numerically robust. And we've tried to improve some of the algorithms for, say, intersection and arc length and things like this, things you want, operations you want to do to a path. A lot of work has gone to make these numerically very robust. So there are fewer surprises when you're working with Asymptote. But the biggest thing really is the generalization to 3 dimensions. There's native 3D support built in to Asymptote. And first thing we had to do was to generalize these, and I'll talk a little bit about that today. Since John Hobby and Donald Knuth are both here, I think it might be interesting to see my take on how to do this generalization to 3 dimensions. There's some arbitrariness, but it seems like a reasonable solution, what we've come up with. Then I want to show you how you can actually embed now lift TeX to 3D and embed it within PDF files so it's fully interactive. And you can have TeX labels that always face the camera if you like, or they can be embedded into the figure. So it is portable. It runs under the major platforms out there. The current statistics are there's about 4,000 downloads per month. That's from the primary site, or there are many distributions that package this up as well. So we really have no idea how many users we have, but there seems to be it seems to be quite popular. There's some statistics on the code. It's half written in C++, and then the higher level stuff, most of the graphical stuff, the detailed stuff, is written in the language which is implemented at the C++ level. This is very much like Emacs having a Lisp layer where some of the Emacs code is implemented in. Okay, and this makes it easier for the user to go and modify this code. It's more difficult to modify the C++ code. And the latest stable release is version 2.00. We expect that, or possibly 2.01 will be coming out in the TeX Live 2010 distribution. Now, just let me give you a little quick tutorial about Asymptote, and then I'll get into the 3D stuff. Okay, so this is just 2D Asymptote, the original version that we released in 2004. There's 4 principal commands: draw, label, fill, and clip, and these translate into PostScript operations. And you see this with following very much the spirit of Metapost, except we use a C++-like syntax, so it looks like a function call. The units here are PostScript big points, which is some approximation of a real tek point. And this dash dash means join those 2 points with a linear segment to create a path. And you can also have a cyclic path, so you don't need to specify this final point. And however, I want to point out, so far everything's like MetaPost. But here's what's different than MetaPost is that I find PostScript units that are pretty inconvenient as a mathematician. You know, I like to work on a unit square, something like that. So here's a unit square. That's the same. This is rather than having to hard code numbers like 100, 0, I can use my preferred user coordinate system, the unit square, and then afterwards tell it I'd like to figure, because of the journal constraints that I want to publish this wonderful figure in, I want to make sure that it's no more than 100 units, PostScript units, big PostScript units, wide and 100 high. Or you can specify the size in centimeters if you like. So there's a way of doing that. And you can also, there's a built-in, this is a built-in path, so you can just call it unit square. And then you can do things like transform that unit square if you want to get a box or something like that. You can scale it or something. You can also add labels. So this is the second command I want to tell you about, second of the 4 commands. And it's very easy to draw labels. You don't have to do any of this BTEC, ETEC stuff anymore. You just put your text string, maybe you want it in math mode, and you label this. It uses compass directions or arbitrary, you can specify an arbitrary vector there if you want to go at some other angle relative to that point. So this is an alignment. It says to align this label to the southwest of the origin, etc. So now if you want to draw a curve, we follow MetaPost very closely here. We use ... if you want to draw curves, and then you specify 2 control points. So this is a Bezier cubic spline with nodes Z0 and Z1. I'm sorry, I have to say Z0, don't I? Oh. And these control points tell you what the outgoing tangent is and the incoming tangent, and how far along they are along this path tell you something about the velocity along there. And this is the actual curve, the blue curve here. And as you know, that's being drawn here. And as you know, the Bezier splines are very useful. They render very fast because they have this midpoint property. So they're widely used in computer graphics. So then the question is, if maybe you don't know the control points, though. Maybe you only know the nodes, and you want to know what the control points should be to get a pleasing-looking curve. There's many ways to do this. But what Hobby and Knuth tried to do in '86 in discrete and computational geometry, that was Hobby's paper, he argued that what you should try to do is minimize the curvature. Well, he didn't really minimize the curvature. It was a mock curvature. It was something that was easier to compute. And he came up with a tridiagonal system of equations that you had to solve. And I'll tell you a little more about that later. But in the end, what he does is try to compute these missing control points so that you get a pleasing looking curve. So now there's 2 more operations, filling and clipping. So let me quickly tell you about them. Here's a star I've drawn. You see the language that has a C++-like syntax. And you might want to fill that star with the 0 winding PostScript rule or the even-odd fill rule. Okay, so you can have different ideas of of insidedness, different definitions of insidedness according to PostScript. And you can also specify a region to be filled by specifying 2 paths like this. And so this is the concept of a PostScript superpath, which is lacking in MetaPost. Clipping, a picture can also be clipped just like in MetaPost. You can do clipping. And you can also, like in MetaPost, you can apply affine transformations like this to objects. You can apply them to pairs, paths, pen strings, and even whole pictures. And I should add, you can also apply them to triples as well. But here I'm just talking about the 2D case. So triples are the 3D analog of pairs. So there are, just to give you an idea of the sort of things people are doing with this, there are modules for Feynman diagrams, data structures, algebraic knot theory, scientific graphs with secondary axes and all kinds of features, logarithmic axes, images, contours, multiple graphs, and all this was computed. There was a specified size, and everything had to be, the length of these lines was computed by a complicated algorithm, actually using the simplex method. Given the size, one had to figure out how to fit everything in. And you see there's different line lengths based on the length of text here. So this asymptote has to communicate with TeX to find out the length of these strings. And it does that by opening up a pipe to TeX and querying it on the width and height and depth of the TeX box that it's dealing with. Of course, TeX doesn't know anything about the fonts, but that's enough information for the preliminary pass. And there's and then the final pass of asymptote, all it does is produce a LaTeX file. At least in 2 dimensions, that's all it does. It produces a LaTeX file for you, runs it through LaTeX, or your favorite version of TeX, ZTeX or Context. These are all supported as well, plain TeX as well. But that's all it's really trying to do in 2D, is it just produces a LaTeX file for you. In 3D, the situation is different, because there's no version, I'm not aware of a 3D version of TeX. So we had to work around that. But first of all, let me tell you a little bit about Hobby's 2D algorithm for picking the directions. So if you're given 3 points, zk minus 1, zk, and zk plus 1, you don't even know, if you want to draw a nice smooth path there, you don't even know what the directions of the path should be at those nodes. You don't know the tangent lines. And so here is Hobby's prescription that the incoming, this is the incoming angle relative to the straight line between the previous node and the current node. The incoming angle, phi, and the outgoing angle, theta, also measured relative to the straight line. It's a straight line deviation of the curve, basically it's a deviation of the curve from the straight line in terms of angle. They should be related by these equations here, where LK and LK plus 1 are the lengths of these line segments. So that's basically what his formula boils down to. You can modify that formula by specifying optional tension and parameters and curl boundary conditions, but this is the default. And then once he has the directions, you can, by the way, this is only for directions that you haven't specified. You might want to override some of these specifications, so these computations here. And you certainly can do that, just as in MetaPost, same syntax almost. Once you've got those directions, then you have to find the control points. You know that the line on which the control points lie, but you don't know how far away they lie, how far to go along here for those control points. And so this is the formula that he used to find U and V, the 2 control points that will define this blue curve here. And this function f is a complicated, messy function. It's given on page 131 of the Metafont book. I refer you to that, or to Hobby's paper. By the way, you notice the exponentials appearing here. Just as in MetaPost, we treat pairs as being complex numbers. It's maybe a surprising thing at first, but these algorithms show you that it's a useful thing to do. So how do we do the 3D generalization? Well, we basically exploit the fact that Hobby's algorithm is always applied to a consecutive list of 3 nodes. And between any 3 nodes, there's a plane. Except there's degenerate cases, which I won't discuss here. But you can always find some plane anyway. And it turns out that what we do then is just apply Hobby's algorithm piecewise on these planes to compute exactly what he would have done on each of those planes. And this way, by doing this, we guarantee that our 3D algorithm reduces to what you would expect in the 2D case. And that's an important constraint, because we're trying to generalize 2D here. The only ambiguity that can arise is in the overall sign of the angle. So when you're in a 2D plane, you don't think about the fact that you could view this from below, or you could view it from above. And that's going to cause some orientation confusions. To sort those confusions out, you need a reference vector. And you can construct one. And we arbitrarily construct it based on the mean unit normal of successive segments. And that's discussed in these papers. I'll give you the reference at the end. By the way, this is downloadable from the Asymptote website. I meant to mention that at the beginning. this lecture, even if you want to follow along now, you just click on lecture if you go to the Asymptote website, which is on SourceForge. The 3D control point algorithm, so to develop that, what we had to do was re-express Hobby's algorithm, just slightly. I'll just go back to it here. Here he's got a vector here, z1 minus z0. Now, if I take the length of that vector and combine it with this direction, this unit vector here, EI theta, then I get, I can write it like this in terms of, I can rewrite it in terms of the length of a vector here. And by doing this, it was naturally clear how we simply interpret theta and phi as the angle between the corresponding path direction vector and z1 minus z0. So just by taking a dot product in the arc cos, you figure out what that angle is. And here, fortunately, there is an unambiguous reference vector for determining the relative sign of the angles phi and theta. So we don't have an orientation issue for picking for the second stage of Hobby's algorithm, where we figure how far along in the direction of the tangent, how far along should the control points be placed. Okay, well, let's show you now some results. Here's our first test of this algorithm, the new 3D algorithm. We're going to try to draw a circle. Well, it's not really a circle, but it's an approximation to the circle, and it'll be it's valid to something like 0.05%, which is certainly good enough for graphics, and just as in following MetaPost. Okay, so here we are here. Just click on that to load the graphic, and then you can see what we've got. 3 dimensions. We can zoom in. So that's pretty neat that you can do that. This is just a PDF file, so you can do this, download it yourself, and do this on your own. But you need version 9 of Adobe Reader to do this. There's no other tool out there yet for reading the PDF files, although we provide enough tools with Asymptote. When we learned the way we learned how to write the 3D PDFs is we first learned how to read them. So we actually do have the tools there that somebody could easily take and hook up to your favorite OpenGL renderer. Okay. And so here is now what happens if you lift 2 of those 4 points, those control points. That circle was drawn with 4 nodes. They're specified there. If I lift some of them up, then I get a saddle like this. And you can zoom in on it here. Okay, so that's enough of that. What about tech? How did I lift tech to 3D? Well, my colleague, a student of mine, Orest Shard, he did a wonderful job in figuring out how to turn the outline information that is reported from GhostScript when it processes the output of DVI-PS. We get the font outlines, but we had to fill them. And that turns out to be a difficult problem because there's no fill operation in 3D. However, you can draw surfaces, Bezier surfaces, but they're patches, and they had to be, the Bezier patches have 4 nodes, 4 corner nodes, and then they have a total of 16 control points. But basically, we had to split this up into quads, if you like, but they're curved quads. Okay, so you could think of this as by doing triangulation. In fact, you see this weird word, bezulate. We're triangulating, but they're curved triangulation, so we call it bezulation. Kind of a strange word. I don't know when it's going to enter the dictionary. Here, just to show you that we really have now tech in 3D, and it looks nice and smooth, and it's really vector graphics. Let me just click on here and just zoom in on something here. Oops. Yeah. Anyway, you can see. So we really have beautiful, smooth graphics where you can zoom in arbitrarily. Okay, so that's kind of neat to be able to do that. And, now, why would one do that? Is that just because it looks cool? Well, the real reason is that I do a lot of scientific computing and fluid dynamics. I do a lot of 3D drawings, and I need graphs to draw graphs where there's labels and sometimes they're Greek labels that I want, and so and I want nice looking fonts. And it turns out in the 3D graphics world, most of the fonts we see are bitmaps or are polygonal. They look horrible, and plus you can do features like this. So here's the difference between a billboard. So I got a cube here. Look at that billboard label. See how compared to the embedded one. You see the problem with if you're going to draw a 3D graph, at some angles you can't see your labels anymore. Okay, so this is a very useful feature, having the billboard. It's an option. You can do anything you want. Okay, here's an example of a 3D graph that one might want to draw, and it just shows you the smooth, very smooth surfaces one can draw here. Okay, and you can see the tech labels that we're drawing here. These are all produced by tech. So that's another example. And here's some arrows. I think this blue arrow is the tech, is coming from tech, actually. That's how we drew that, and we somehow managed to lift that into 3D. That was kind of fun. But then we have a rotational arrow and a planar arrow here. Sometimes people prefer, if they're going to print a book, or sometimes they prefer, eventually it's going to be 2D, they prefer to have the arrow just planar and not worry about what's going to happen if you rotate it and then it looks like that, right? That's the only disadvantage with a planar arrow, whereas the cone isn't going to do that. Yeah. So there's all kinds of issues you have to think about. Anyway, this presentation was prepared with Asymptote itself. So here's the slide presentation module. One of the advantages of this module is you can do things like embed these 3D PDFs right in. And you can also have high-resolution PDF movies. This is not lossy, unlike MPEG movies, so that's kind of neat too. And finally, a little bit about the sizing. I talked about, I mentioned that Asymptote has this automatic sizing. The point is that when you publish something in a journal, there's usually some restrictions on how much space you can take. And yet, some parts of your diagram are things like fonts, which the journal says have to be at 12 point or whatever. And maybe you have line widths; they have to be a certain width, and these are fixed. Arrowheads, perhaps they are fixed as well. Well, you can decide on all these things, which things should be fixed and which things shouldn't. And then, depending on the size that the journal gives you, if they're really skimpy, they only give you this little room here, or maybe they give you more room. You want to draw the best figure you can to fill that up, okay? And so this is not a completely trivial problem. It's linear, fortunately, but it does require it requires, first of all, queuing. You cannot draw anything until you actually know the scaling, until you have all the information. So everybody's experienced this when you draw a graph of several curves, and you don't know where to plot the curves until you have them all in memory, and then you can go and plot them. It's the same issue here. Asymptote uses high-order functions. You can pass functions around as objects. In fact, functions and variables are treated on an equal footing. It's very nice, but it still allows operator overloading of functions and variables. So anyway, this is the kind of deferred drawing. I don't think I can take too much time to explain too much what's going on here, but this is the queuing thing. It's saying add to the picture routine that is going to draw. It's not going to return anything. It's just going to draw on a frame. A frame is like a canvas for drawing. And it's going to draw using this particular scaling here. And so with the user's path that's given in user space, I have to first scale it by multiplying it by this transformation on the left. But I won't do that until later, so I'm just telling it, keep that around for later, okay? And it has to keep track of the difference between user coordinates and true size coordinates. For example, you draw a path. Well, that path has some thickness. Presumably, you have a thickness to your pen. And so, although the path will scale, the pen width won't. And you've got to keep track of all that, and that affects the bounding box of the final object. And so we keep track of these two kinds of coordinates: scalable user coordinates and true size coordinates. And as I said before, we communicate with LaTeX or whatever version of tech, whatever tech engine you're using. We communicate with via pipe to determine the label sizes. So that's how we were able to put that box around that wonderful formula. So there are constraints that we have to satisfy to do that, and we use the simplex method to resolve these constraints. They're just linear inequalities, fortunately. So it's a straightforward linear programming problem. However, you get a lot of constraints typically, but you only keep the maximal constraint, the one that there's often a dominant constraint that dominates some of the others. Here's an example of how deferred drawing is very useful. If I want to draw a picture like this, but then I want to draw these infinite lines here, connecting points P and Q, for example. I want to draw these, they're infinite lines. I want to draw them to the boundary of the picture. I don't know the boundary until I've done the drawing, right? So that's where it's useful. So this comes up in elliptic curve cryptography. And there's just a couple things that we decided were useful. I think it's a nuisance to a lot of people in a lot of language. The integer division returns an integer. Why not make it return a real? That saves you from a lot of bugs. It's happened to us, everybody, so many times. If you really want, in the few cases where you do want integer division, there's a function for it. We use a caret for exponentiation, and there's implicit scaling of numeric constants, which is sometimes convenient for writing 2 pi and 10 centimeters, for example. And as I mentioned, pairs are complex numbers. Okay, so that's a true statement. And function calls are very nice because, unlike C, the default arguments can be in any position. We figured out a way of doing that where it uses the type to resolve any ambiguities. And so, for example, if you say here, draw ellipse 2, the 2 matches the first argument, the x size there, and so, and it doesn't, no pen was specified, so it uses the default, which is blue. So it draws a big ellipse 2. Of course, it's a circle, and that's because y size is automatically set to be x size, so it's also 2. Okay? So what this is doing, drawing a unit circle and scaling it by y size and scaling it by x size. But both x size and y size are 2 here. But here, they're both 1, and it's red. So that's why we have a small red circle, etc. Okay? And this is another example where we're getting an ellipse with different sizes, but same idea. And so these are higher order functions I had mentioned that you can pass to, say, a graphing routine. Okay? And that's often, in the C language, this is often a nuisance, right? Okay. So in summary, Asymptote uses IEEE floating point numerics, a C++-like syntax. It supports deferred drawing for automatic picture sizing. It supports a number of popular color spaces, PostScript shading, pattern fills, function shading. That's only available in PDF. It's a PDF feature. It can fill non-simply connected regions, and very importantly, it generalizes the metapost path construction algorithms to 3D curves and also surfaces. And it lifts tech to 3D. And as I showed you, it supports 3D billboard labels. I didn't show you the PDF grouping, but maybe I can just go back to an example and show you that. If we take a 3D, why don't we take this one here? Okay, so if I can find it again. There we are. Oops. No, I'm not touching the touchpad, but it's just Adobe is a little slow sometimes. Okay. Okay, now what I'm trying to do here is show model tree, and then it doesn't help that the podium here is slanted, so my mouse slides down. Oh my, let me try to look here. Come on. Well, I'll just have to open up here, and you're going to just have to see there's not very much space here. But you have a tree here. I'm trying to make this bigger. And so we'll go down to the bottom one here. First of all, let's just see what that is, turn it on off. That's an axis there I'm turning on and off. And you can see, we can go in to see what's inside that axis. There's a curve. There's the curve. And there's a tick. There's a tick right there, turning on and off. And then there's some labels. There we are. I turn the 2 on and off. Okay. And how about the axis label 2? Turn it on and off. And you can see it actually tells you what the text string is there. So that's a new feature that's in the recent versions of Asymptote. So that's all I have to say. Thank you very much.
Questions, please?
Hi. Okay.
Yeah, actually, I wanted to applaud all the way through, but I got three questions. First, do I understand correctly that the output is to PDF?
The output is, the native output actually, oh yes. The question is whether the output is PDF, and it produces PDF, but the default is actually EPS, the PostScript, and it can also produce scalar vector graphics.
Okay, many different.
Yeah, so those are the various possibilities.
Okay, so is it an interpreted language or compiled?
It actually is compiled. There's a virtual machine running, but it gives you the feel of an interpreted language because you can type in a command and it'll execute it, give you the result. But it's actually compiled that, and it's done in a very, very clever way. Not by me, it's by my student. I have some excellent, very excellent students who've written the virtual machine. Yeah.
Okay. And then you said you solved something by the simplex method, but that doesn't give you a unique solution. What did you mean?
Well, most of the time it does. If it doesn't, it's in this particular case, the times when it doesn't is because you haven't specified the problem. You specify an ill-posed problem. An example would be if you draw just a horizontal line, and that horizontal, because it's horizontal, it has no height, but there's a pen width, but you specify that you want now the diagram to be 1 centimeter high.
We're talking about different things. You had a bunch of linear inequalities.
Right.
So that in general, that's solved by an n-dimensional. I mean, you've got a family, some convex polyhedron.
Right. And
so which point in that convex polyhedron is the solution?
well, the solution should be a vertex on that polyhedron.
And you just take any vertex and say that's okay? There was no objective function, as far as I saw.
Yeah, maybe it's something we should talk about after.
Okay. I mean, usually you're minimizing or maximizing something.
We are trying to we're trying to basically maximize the picture size. I think that's the objective function. Yeah.
Other questions? Just overwhelmed? Is that so can we thank our students?
Okay, thank you.